Okay, it's a great pleasure now to introduce our keynote speaker for today, Salil Vadhan. Salil is the Vicki Joseph Professor of Computer Science and Applied Mathematics at the Harvard John Paulson School of Engineering and Applied Sciences and lead PI on the Harvard Privacy Tools project. His research in theoretical computer science spans computational complexity, cryptography, and data privacy. He's a Simons investigator, a Harvard College professor, and an ACM fellow. He's received many honors for his work, including in particular the Gödel Prize and the Guggenheim Fellowship. Salil may not remember this, but I first heard him give a talk many years ago on pseudorandomness at a theory colloquium at MIT. I thoroughly enjoyed that talk. Today, Salil is going to talk to us about the theory and practice of differential privacy. This is a topic that has received increasing interest in the COLT community in recent years. And so we're especially delighted to have you join us here today, Salil.
Thank you, Shivani. Please let me know if anything is going wrong with please interrupt me with the video or the audio. Is this all coming out clear?
Yes, we can hear you.
Yes.
I hope
okay.
That too.
All right, great. So thank you, Shivani, for the kind introduction, and Jacob and the PC for having me, and all of you who are attending. I hope all of you and those close to you are staying safe and healthy in the face of the pandemic. I'm honored to have the opportunity to give the first invited talk on differential privacy at COLT, which is really long overdue, given that a lot of the great work that's happening in differential privacy is happening right here in the COLT community, as is evident even just from looking at this year's program. So to give you a sense of the perspective that I'm coming from, as Shivani mentioned, I'm also a complexity theorist, and I started working on differential privacy really as a complexity theorist, trying to understand the limits of what's possible and impossible with differential privacy. And most of my early papers were lower bounds and hardness results. Increasingly over time, I became interested and involved in the practice of differential privacy. So much so to the extent that we're now launching a large-scale open source software project around differential privacy called OpenDP that I'll mention later in the talk. And what I've learned through this, and part of what I want to convey in today's talk, is that the theory and practice of differential privacy are quite aligned. And indeed, the needs of differential privacy in practice raise many fascinating questions for theorists to tackle, some of which I am going to try to highlight in the talk today. So let me begin with a very brief review of differential privacy. Differential privacy aims to enable statistical analysis of data sets while providing strong guarantees that individual level information does not leak. It achieves this by carefully injecting small amounts of random noise into statistical algorithms to obscure the effect of each individual data subject. The reason we need differential privacy is that traditional methods for protecting privacy are now understood to be inadequate and are vulnerable to worrisome attacks. These include re-identification attacks on supposedly anonymized data sets, as well as more sophisticated attacks that apply even to releases of what seem to be aggregate statistics. These include database reconstruction attacks, where an adversary takes the release numbers and somehow combines them to reconstruct almost all of the sensitive data from what's released, as well as membership inference attacks, where an adversary can determine with high statistical confidence whether someone is in a sensitive data set or some sensitive subset of a data set. These attacks are not just theoretical possibilities. They have been demonstrated to work on actual data releases and machine learning systems, and this has motivated much of the use of differential privacy in practice, including by the US Census Bureau, as I will mention later. Differential privacy, just to hammer this point home with a nice example, also protects against the phenomenon that you all may be familiar with, that deep learning models sometimes inadvertently memorize some of their training data. And this is something that, for example, Reddit users discovered a few years ago by entering nonsense into Google Translate. And what happened is that they got back passages from the Bible, which had been verbatim and memorized by the deep net during the translation. All right, so this may not be so much of a problem if you've used passages from the Bible as your training data, but imagine a translation system trained on emails or text messages. So with that motivation, let's recall the definition of differential privacy, which developed over a series of works starting in the early 2000s, culminating in the celebrated paper of Dwork, McSherry, Neesman, and Smith. So consider an interface to a sensitive data set, which we'll refer to as a curator, denoted C, which fields queries from external analysts and provides randomized answers. Differential privacy requires that let me go back for a moment, that the effect of each individual data subject, that is each row in the data set, is hidden from the outside observers. So more specifically, we imagine an adversary interacting with a system, possibly deviously issuing queries, trying to learn information about a particular individual in the data set. And differential privacy requires that the adversary should not be able to tell the difference between the responses it gets and the responses it would have gotten if we remove that person's data from the data set and possibly replace it with arbitrary other values. Right? So from the adversary's point of view, it's as if that individual was not in the data set at all. Formally, what we require is that for any two data sets, D and D prime, that differ on one row, on one individual's data, and any sequence of queries that's issued to the differentially private system, the probability distribution, the joint probability distribution of results that are seen by the adversaries is close under D and D prime. How close the distributions are is measured by two privacy loss parameters, epsilon and delta. Epsilon measures the multiplicative relationship between the distributions, and we typically want it to be bounded by a small constant, like 0.1, whereas delta should be extremely small, negligible in cryptography terminology. Sometimes I'll omit delta from the notation and just refer to epsilon dp, but throughout the talk, I'm referring to this epsilon delta differential privacy unless I explicitly say otherwise. As most of you have probably seen, simple statistics like counts or averages of bounded functions can be released in a differentially private manner by simply adding a small amount of random noise to the true answer. So for a mean or a population fraction like this, what fraction of people in the data set have certain properties, we can compute the true answer and add noise on the order of 1 over n, where n is the size of the data set, the number of records in the data set. And the reason for that is that each individual's data affects the true answer by at most plus or minus 1 over n. And so if we add a bit more noise than that, we can obscure the effect of each individual. And how much larger than 1 over n we need is governed by the privacy parameter epsilon. Okay, and to meet the formal definition of differential privacy, it's important what noise distribution you choose, and a common choice that achieves what's called pure differential privacy with delta equals 0 is the Laplace distribution. Okay, and the point is that the amount of noise that you need to introduce vanishes as the size of the data set n tends to infinity, and in fact vanishes more quickly than the uncertainty we expect just from sampling error in the true answer, which vanishes on the order of 1 over square root of n. That was just for answering one query. For many queries, differential privacy has nice composition properties that allow us to reason about how privacy degrades as we answer multiple queries. And specifically, if we run k independent differentially private algorithms, each of which has some privacy loss parameter epsilon naught, we can bound the privacy loss of the resulting algorithm by the original privacy loss times a factor that's roughly square root of k, square root of the number of queries. And we can then compensate for that by just adding more noise to each of the individual queries, increasing our noise by a factor of square root of k in the simple example of the Laplace mechanism that I described. So it's worth mentioning, but I won't go into detail in this talk, there's been a lot of great work on giving more refined, in some cases optimal, composition theorems for differential privacy, sometimes using variants of differential privacy, like you may have heard of concentrated differential privacy, Renyi differential privacy, and Gaussian differential privacy. Of course, I've only given the simplest example of a differentially private algorithm. And already, when I first made this particular slide 6 years ago, there was already a rich algorithmic literature on differential privacy showing that many things that we want to do in data analysis are compatible with it. And the literature has only exploded since then, and it's hopeless for me to try to give a comprehensive survey of it all. So in addition to lots of advances in the science and theory of differential privacy, we've seen a number of exciting deployments of differential privacy in government and the tech industry. The highlight of which is the US Census Bureau's landmark decision to use differential privacy for all of the public use products it releases from the current 2020 decennial census. In the tech industry, we have large tech companies like Google, Apple, and Microsoft using differential privacy to collect data from users, and have also developing methods to train machine learning models in a differentially private way. From the academic research community, there have also been many wonderful advances in tools for differential privacy. However, these often stop at being research prototypes that are built by one group, don't integrate with tools from other groups, and don't ever make the transition to trustworthy production code. The same is, of course, true with the work that I and others in our group at Harvard have been involved with in the Privacy Tools project that Shivani mentioned in the introduction, which we've had going since 2012. This project is how I got interested in the practice of differential privacy, as it gave me an opportunity to interact with our colleagues in the social sciences who had a real need for safer ways of sharing sensitive data sets. Towards trying to improve the state of affairs in differential privacy tools, we've recently started this project OpenDP, which is meant to be a community effort to build a trustworthy and open source suite of differential privacy software tools that can be easily adopted by custodians of sensitive data to make it available for research and exploration in the public interest. So the goal is to channel the many advances the differential privacy community is making on the science and practice of differential privacy, with the idea that by building software together and vetting each other's code, we can obtain tools that are more trustworthy, provide greater utility, and have a larger impact. We can foster greater adoption of differential privacy to address compelling use cases, and we can provide an advanced starting point for custom DP solutions where they're needed. So I want to stress here that in OpenDP, we are focusing on use cases of differential privacy of sharing data for research purposes in the social and health sciences, for example. All right, and so whether that's researchers sharing data they collect with each other through research data repositories, or companies or government agencies making data available to researchers or the public. And these use cases and the challenges that are confronted in them motivate the choice of research challenges that I've chosen to highlight in the rest of this talk. But in the other direction I want to mention, I believe that this effort to bring differential privacy to practice is going to uncover many important and fundamental research questions for research on differential privacy. Okay, briefly, just I will also mention, since there are talks of both types in this year's COLT programs, in this talk, I am focusing entirely pretty much on what's called the centralized model for differential privacy, where a trusted curator holds all of the sensitive data and makes releases on it. Some of the industry deployments of differential privacy for collecting data from their customers are in the more stringent local model, where the individual data subjects introduce noise before sending it to the curator that computes statistics. This is a very attractive model for those sorts of applications, but has a significant price in terms of the accuracy that's possible. Okay, so in the rest of the talk, I'm going to talk about 3 active areas of research in differential privacy, where learning theory plays a significant role and there remain some major challenges. Differentially private statistical inference, differentially private synthetic data generation, and differentially private machine learning. And I'll start with differentially private statistical inference. So this would be a good place to pause if there are any clarification questions so far. Okay, so let me jump into differentially private statistical inference. So it's wonderful to see already 4 papers, if I haven't missed any, in this year's COLT, many of which were in the session this morning that I enjoyed hearing about. So it is an active area that this community already is familiar with. But let me kind of, since those talks only have these 1-minute presentations, try to give sort of put it in a higher level context of the state of the field of differential privacy. All right, so, you know, I, again, come from kind of the core kind of traditional theoretical computer science, and our traditional modeling in theoretical computer science and algorithms is that we have some input X, that's our object of study, and our goal is to compute something about it. And so the utility or objective function measures the quality of our output Y with respect to X, which is typically a worst case input. As you all know, in statistics and machine learning, the real object of interest is not the data or data set, but it's the underlying population from which the data set is drawn. And what we really should do is measure our utility with respect to the population as opposed to the data set. Much of the early differential privacy literature, for good reasons in terms of a starting point, inherited the first view, the traditional TCS view. However, as you might imagine, for making data available for research purposes and many of the other applications of differential privacy, it's the latter that is really what's needed. So I want to just kind of stress here, one point is we are going to maintain here the requirement of differential privacy as a worst case requirement over data sets and neighboring data sets, ones that differ in one individual. Since we don't want privacy to fail because our modeling is wrong, or that we don't model the distribution of the data, or even more importantly, don't try to model the adversary's knowledge about the data set. And we don't want mistakes there to translate into violations of privacy. So we have a worst case definition of privacy, but utility, how we measure how accurate or effective our algorithm is, should be an average case measure. Okay, and so we want that to be average case, kind of over the data set sampled from the population, and with respect to as well as the noise introduced for privacy. And with respect to the population, it may be a worst case. We may do worst case analysis over or minimax frequentist analysis over the population, or we may assume some prior distribution on the population parameters in a more Bayesian approach. And so already this was present in some of the early works on differential privacy. And one that stands out in particular is the paper that started the study of differentially private pack learning by Kasiviswanathan, Lee, Nissim, Raskodnikova, and Smith, often referred to as the Cleaners paper for short, which is a paper that I will talk about a lot. That's an important paper that I'll talk a lot about in the last part of the talk. Okay, so what's a natural approach to kind of doing differential privacy, statistical inference with differential privacy? Well, a very natural thing to do is to say, well, let's take the best non-private inference procedure we know and then try to make it differentially private. Okay, and so for example, if we are trying to just do something very simple, like estimate the mean of a population, we know in the non-private case that the sample mean is in many ways, in many senses, the best estimator for the population mean. And in particular, it converges to the sample mean at a rate of about 1 over square root of n. Okay, and then the next step is to say, okay, take this non-private estimator, like the sample mean, and try to produce a differentially private approximation to it. And so as we saw before, when we're computing means or averages, one easy way to get differentially private algorithm, simple way to get it is to simply add noise to the result, and we add noise on the order of 1 over n. Okay, and as I mentioned before, this is going to 0 more quickly than the sampling error. And so it looks like we're getting privacy for free. We're having a differentially private estimate that converges to the population quantity of interest, at a rate that's like 1 plus little o of 1 times the convergence rate of the best non-private estimator. Unfortunately, those asymptotics where we focus only on the dependence on n can be very misleading. So for example, if we look more closely, the convergence of the sample mean to the population mean has a factor of sigma, the standard deviation in it. And the noise for privacy is not just 1 over n, but it has the privacy parameter epsilon in the denominator. And it also, I said, we could just add noise in the order of 1 over n for bounded functions. But, and so the bound that we have on the range of our data also appears here in the amount of noise we need to add for privacy. Okay, and so we get that the noise for privacy is dominated by the sampling error only when n is at least the square of the product of all of these quantities, which can often be very large. Okay, and even worse, we don't necessarily know when the asymptotics have kicked in, because sometimes these parameters, like the standard deviation sigma, are population parameters that are unknown. And the result is that if we just naively apply differential privacy, you run into a situation where analysts can draw wildly incorrect inferences at finite sample size because the asymptotics haven't kicked in yet. Furthermore, taking this two-step approach may not also be the best way to get the best convergence rates for differentially private estimators. That it may not be the case that that it may be that a suboptimal non-private procedure is more amenable to being converted to a differentially private algorithm, and thus leads to a faster convergence rate, right? And so, for example, several works have found that estimators from the robust statistics literature, so estimators that are not so sensitive to outliers, for example, ones based on medians or ranks, often yield better differentially private algorithms, even for the case where you normally wouldn't need to apply robust estimators, where your data is very nice, for example, coming from a normal distribution. All right, so it does better than standard like mean-based or for regression, better than ordinary least squares in many settings to use robust estimators. Okay, so what does this tell us? So first, we should study the overall design problem of not trying to break things always into these two steps of designing the optimizing differentially private algorithms specifically for statistical inference and optimizing how well we estimate population parameters. And second, it's crucial for the applications of differential privacy that we design differentially private algorithms that also produce measures of uncertainty, like confidence intervals or p-values, that take into account both the random sampling as well as the noise introduced for privacy, to make sure that analysts making use of differentially private data don't have false discoveries as a result. Okay, so as I mentioned, as reflected in this year's COLT program, there's a lot of great work happening on differentially private statistical inference, but there's still a lot to be done, even for very simple inference tasks like mean estimation or simple univariate linear regression. For example, we'd like tighter bounds on the error or sample complexity without extra constant or polylogarithmic factors. So in particular, we'd like to really understand when can we say that differential privacy is for free, the differentially private estimates are nearly as good as the non-private estimates within 1 plus little o of 1, not just within factors of 5 or 50. Second, most of our methods don't produce confidence intervals in addition to point estimates, and that's something that should become a more active part of what we do in differentially private algorithm design. We also lack a good theoretical explanation of the phenomenon that I mentioned earlier. When is it exactly that differentially private analogs of robust estimators do better than other methods for designing differentially private algorithms? And finally, I said that asymptotics can be very misleading, but in applied statistics, it's very common to use, for example, the central limit theorem to produce uncertainty estimates. So ideally, somehow, rather than dismissing all asymptotics, it would be better to understand and develop an understanding of what kinds of asymptotics are safe in developing DP inference algorithms and which are not. And all of this becomes, of course, more challenging as you move to more complex high-dimensional models. And also, ideally, we'd eventually reach the point of not attacking each inference problem one at a time and optimizing for it, but to really have more general-purpose recipes for obtaining high-performance, near-optimal differentially private inference algorithms. All right, the next direction I'd like to discuss is generating synthetic data in a differentially private manner. So what does this mean? So what I want is a differentially private algorithm that takes a sensitive data set and outputs a data set, a synthetic data set that has the same schema as the original data set. That is, the rows are taken from the same data universe, denoted script X here. And what we want is the synthetic data set to reflect many of the statistical properties of the original data set so that people can use it as a proxy for the original data set. Okay, but it should satisfy the strong property of differential privacy, where no individual data record has a significant noticeable influence on the synthetic data set. So in particular, we can't obtain the synthetic data set just by anonymizing each row of the original data set separately, but rather all the records in the synthetic data set are somehow obtained by a global analysis of the original data set. So synthetic data generation is very attractive in applications. In principle, if we could do it well enough, then we could just publish the synthetic data set and discard the original data set with no need to field queries from analysts or manage or privacy loss budget across multiple queries. And the data analyst workflow doesn't need to change. They can just treat the synthetic data as if the original data were published. So for these reasons, the Census Bureau determined that it needs to produce synthetic data for the 2020 census, or more accurately, publish a set of tables that are consistent with a single underlying synthetic data set. So let's try to understand what we want from the utility of synthetic data. I said we want the synthetic data set to reflect many statistical properties of the original data set. So intuitively, you can think of this as a distribution learning problem. We want the synthetic data set to reflect the empirical distribution of the original data set in some sense. All right, and already here you might notice a discrepancy between what I've just stated here and the previous part of the talk. Actually, what we often really want is the synthetic data set not to reflect the distribution of the data set, but to reflect the population distribution. I'll come back to that a little bit later. So how do we measure the closeness of these two distributions? The standard thing, at least in the differential privacy literature, is to require that some family of statistical queries is preserved. All right, so we have some family of bounded functions, little q here on the rows of the data set, and the family is capital script Q. All right, and what we want is that the average of these functions, so on a data set, so average over the rows of the data set, should be preserved in the synthetic data set to within some tolerance parameter, say plus or minus alpha. All right, so a favorite example that we study a lot in the differential privacy literature is, you have a data set that consists of binary attributes, say some little d binary attributes, and the family of queries are all low order conjunctions on those attributes. All right, and then so the queries averaging over the data set allows you to estimate things like what fraction of people in the data set have some combination of properties, like are smokers and have cancer. Okay, so a series of beautiful works starting with Blum, Liggett, and Roth, and culminating in the private multiplicative weights algorithm of Hart and Rothblum, produce some amazing differentially private algorithms for generating synthetic data that preserves any desired family of statistical queries. All right, so the family queries here is an input to the algorithm. And these algorithms are all based on learning theoretic techniques, such as uniform convergence and online learning, as you can guess from the private multiplicative weights being the name of the Hart-Rothblum algorithm. Okay, and so what does it provide? It takes a data set, and any data set, and produces a synthetic data set with respect to some family of queries that's epsilon delta differentially private, and with high probability over the coins of the algorithm. It holds that for every query in the family, every statistical query in the family, its value on the synthetic data set is close to that on the true data set, to within a bound that's written here, which you can see is like vanishing like 1 over square root of n. And importantly, depends only logarithmically on the size of the data universe and the size of the set of queries. Okay, so in principle, we can generate differentially private synthetic data, preserving exponentially many statistical queries, even on high dimensional data, a data universe that's of exponential size. Okay, and this bound is also known to be tight for some classes of queries, including some natural ones like low order marginals, as the example I gave before. So why don't we see everyone using these algorithms in practice to generate and publish differentially private synthetic data? The problem is that the runtime of the algorithms, as you might expect in such generality, is polynomial in the size of the data universe and the number of queries in the family, statistical queries in the family, which is exponential then in the dimensionality of, at least exponential in the dimensionality of these two spaces. Okay. And unfortunately, that's known to be necessary. Yeah. Was there a question?
There's a small question. Whenever you have a chance, let me know.
Sure.
Okay, there's a question, I think, on the previous slide from Sebastian Gershonowitz. He asks, little question, please. How large is a synthetic data set?
Great. So the synthetic data set doesn't need to be very large. It can be smaller than the original data set. And the reason is that for the kind of accuracy that we're talking about now, which is preserving a class of statistical queries, that is, you can take, even if you had a large synthetic data set, you can subsample it, and by uniform convergence, even if your subsample is only, again, polylogarithmic in the number of queries and the size of the data universe, you will still maintain accuracy. So thanks for the question. Okay, so unfortunately, this exponential, so the accuracy is very, very good, but the runtime isn't. And unfortunately, this exponential runtime in the dimensionality is known to be necessary in the worst case, if you believe in cryptography, even for very simple query families. So what might we hope to do? Well, one hope that has been explored as a continuing area of research is to try to use heuristics, for example, integer programming heuristics, to try to get faster algorithms that are faster in practice, not necessarily in the worst case. Right? And then a key, similar to some of the issues I talked before, what we want is that if these heuristics fail, which they will in the worst case, what we want is that that doesn't cause a violation of privacy. The privacy doesn't depend on the success of the heuristics, but the accuracy might. And ideally also, what we would like is that if the heuristics succeed, we get some certificate. We know that we actually have an accurate synthetic data set that people can analyze effectively. So this approach of using heuristics was pioneered in the dual query algorithm by Gabarty et al. And what it did is, using integer programming heuristics, it brought the runtime down from, changed the exponential, the polynomial runtime dependence on the size of the data universe into polylogarithmic in the size of the data universe. However, it still is polynomial in the size of the family of statistical queries that you want to answer, right? And effectively, you still have to kind of enumerate explicitly over all of the queries you want to be preserved. A recent work of Neil, Roth, and Wu has attacked that problem and brought the dependence on the number of queries down to polylogarithmic. And with the downside that now there's a dependence on the privacy parameter delta, the additive privacy parameter delta, that's polynomial. And that's still infeasible if you take, as I've advocated, delta to be cryptographically small. Okay. So getting rid of that dependence on delta is a fascinating open problem for differential privacy research.
Great. There are two more questions if you have a moment.
Sure.
Okay. So there's one from Mauro Escudero. He asks, has the distance between the original and synthetic dataset ever been measured in terms of KL divergence between empirical distributions of the two datasets, and then bounding this between plus minus alpha?
Great. I believe there was some early work doing experiments like that of Feinberg and others. Asking for KL divergence to be small can be too much to hope for if you're talking about high dimensional data, which is the setting these algorithms that I'm talking about now are designed for. Because for the KL divergence to be small, like the supports have to be the same, and you're going to expect on high dimensional data the supports will be completely disjoint. So maybe one alternative is to look at KL divergence on subsets of attributes or something like that. I don't know if that's been explored.
Great, thanks. One more question from Shai Ben David. He asks, why is the dependence on the size of Q rather than the VC dimension of Q, taking advantage of relations between queries?
Great. So this relates to one of the bullets I have on this slide. Okay, so there's been also a beautiful line of work on trying to characterize the best error possible, or the sample complexity for generating synthetic data, in terms of the structure of the class Q. And things related to VSE dimension come up, but actually, interestingly, the things that have emerged as seemingly most relevant, and in some cases, like for some variants of differential privacy giving the right answer, are geometric quantities such as packing and covering numbers or Gaussian width of a polytope that's defined by the class Q. Thanks for that question. All right, great. So, all right, so let me just quickly mention some of these other challenges before moving on to the last topic I wanted to discuss. So first, you know, as I mentioned in the previous part, what we really want is synthetic data that supports statistical inference. I've mentioned that, you know, because of the same kind of uniform convergence phenomenon that I mentioned in response to the earlier question, that's not a big deal. The difference, there's not much difference between, you know, the empirical distribution and the population distribution if we just are talking about accuracy in terms of the query family Q. Okay, but what about if researchers carry out analyses on the synthetic data set that are outside the family Q, right? In practice, what one imagines, you publish the synthetic data set, and now people treat it like it's the original data set. What can we say about inference for such analyses that are not explicitly in our family Q, or not even, you know, explicitly statistical queries, like someone runs a regression? So that's a really interesting and important question for synthetic data generation. Ideally, we'd avoid even explicitly specifying the family Q, but just ensure that somehow the synthetic data is good enough for most natural analyses. Along these lines, there's been a series of recent works exploring differentially private training of GANs, generative adversarial networks, from deep learning for synthetic data generation. On the other hand, it seems difficult right now, be very interesting if one could, to attach any accuracy guarantees to synthetic data produced in this way, much less, you know, kind of uncertainty estimates that I'm asking for. And then we already talked about the previous one, and then the last one I would like to mention here is that another direction that's been a little bit more dormant in the last 5-6 years is a potential way to bypass some of the intractability is to move away from synthetic data, but produce other forms of statistical summaries of the data set. Okay, so some kind of summary that allows you to still answer all the same queries, but isn't encoded in a synthetic data set. Right? This is something that's referred to as a query release or sanitization problem. And it may be worth revisiting that and see if more we can make more headway on that direction. All right.
Salil, you mentioned one more question to you.
Mm-hmm.
So Sushant Agarwal has a question. He says, and there's another one after this, but Sushant's question is, would making Q public possibly lead to some loss in privacy? He meant along with the synthetic data set.
Great, good question. So not the way these, I mean, so these algorithms are thinking of Q as specified in advance independently of the data. So there is not a privacy risk to the data subjects by making Q public. And the privacy properties are for every Q, it's epsilon delta differentially private. One might worry, and I had a paper with Cynthia Dwork and Moni Naor on this a while back, about what's called privacy for the analyst, right? So think of an interactive system where analysts are issuing queries and possibly fielding queries from different analysts. The analyst may care about the privacy of their query, what kind of research they're doing on the data to be protected from other analysts. And that's also an interesting problem. It's a complementary problem. I don't think we have a complete picture. There's a very nice paper that improved the results from our work. I don't remember all the authors. Aaron Roth and John Ullman are two of them that you might look at if you're interested in that question.
Great, thanks. The next question is from Daniel Severo. He asks, how does the synthetic dataset size come into play in these questions? For example, I think it's related to the previous one that you mentioned already. For example, is there an optimal size of synthetic dataset such that generating points beyond that size doesn't help inference?
That's a good question. I think, you know, the phenomenon here, if I'm understanding the question correctly, is kind of similar to, as it often is in kind of machine learning and inference. So if you look at this, you could first ask, like, what's the sample complexity? How big do I need n to be for the bound to become non-trivial? Say smaller than a half, okay? And that's given by, you know, the rest of the quantities in this ratio here. But as n gets bigger than, sorry, this is the data set, not the synthetic data set. But there's probably something similarly true, right? If you produce too small a synthetic data set, even if your n was very large, you just won't be able to, my guess, capture the accuracy. Or I mean, like a trivial lower bound is, you won't get accuracy to better than 1/m, where m is the number of rows in your synthetic data set. But I don't have a more precise answer to the question.
Okay, thanks.
All right, great. So in the time that's left, let me talk about differentially private classification. Thing that's kind of most, and I should thank Mark Bunn for material and pictures that I've used in a bunch of these slides in this part of the talk. And this was introduced in that Cleaners paper, seminal Cleaners paper that I mentioned earlier. Okay, so here, it's like in the setup we had for statistical inference. So there's some population from which we have a random sample of labeled examples. And now we want a learning algorithm that's differentially private, say epsilon delta dp, and it outputs a hypothesis, H, that should classify well on the population. And since I'm assuming this audience kind of knows, I won't all the sort of formalism associated with classification, I'll jump straight to talking about what kind of questions might we ask about it. So one, of course, we might ask, how is this problem related to other problems in differential privacy, in particular the synthetic data generation problem that I talked about before. And there we can see that private classification is in some sense no harder than synthetic data generation. In particular, if I take I have some data set with positive examples and negative examples, at least so binary classification, and I produce a synthetic data set on from the positive examples and a synthetic data set from the negative examples that's good with respect to our class of queries that's the same as our concept class, then I'll get a new set of like synthetic positive and negative examples that is just as good for learning as the original data set with respect to this concept class. And I can publish it in the clear, and I can just run a non-private learner on it. Okay. There's some small issue that you may lose realizability. Perfect realizability may become almost perfect realizability when you do this. A second thing is we can ask, what's the relationship between differentially private learning and non-private learning in general? And you can ask that, for example, in the PAC framework of learning. And we can ask, does the requirement of privacy increase the sample complexity for learning? Does it increase the computational complexity for learning? And then we can also ask about what about differential privacy outside for machine learning outside the PAC framework, such as deep learning. And here the answer is also, it's positive that the main method that the standard training method, namely stochastic gradient descent, is very compatible with differential privacy. Intuitively, because each gradient is itself an average or mean computation to which we can add noise at each iteration and use composition of differential privacy to obtain an overall differentially private version of stochastic gradient descent. And this is the basis of the differentially private version of TensorFlow developed and released by Google a few years ago. So in the rest of the last few minutes of the talk, what I'm going to focus on are questions of the sample complexity of differentially private PAC learning. And compared to the rest of the talk, this part is more driven by purely theoretical considerations rather than the practice of differential privacy. And in particular, I'm going to ignore computational complexity considerations. And the reason for focusing on it is that there's been a number of exciting developments very recently. As a motivating example, let's consider the problem of learning threshold functions, say one-dimensional threshold functions. And for reasons that'll become clear later, I'm going to restrict to a finite data domain, say the numbers from 1 to t. So that's the discretized domain. And we have this concept class of threshold functions. And let's say we're given some data set that's sampled from some distribution. I have my positive examples and negative examples. And since I'm focusing on the realizable case, there is some threshold that correctly classifies all of them. So all the positive examples are below all the negative examples. Right, but I don't know what this threshold is. So the simple non-private learner would be to just take, say, the largest positive example and use that as our threshold, as our hypothesis. This has perfect classification on the training data, zero training error. And then by standard kind of uniform convergence arguments, that if our sample size is big enough, can also deduce that this hypothesis will also have very high accuracy on the population. And importantly, for what I'm going to say later, the sample complexity that I need depends only on the accuracy parameter and the confidence parameter alpha and beta, and they don't depend on the threshold t. Indeed, one-dimensional thresholds can even be, this learner works even over an infinite domain like the entire real line. Okay, however, it's not differentially private. As you can see, if I, one thing it's doing is revealing the largest positive example completely in the clear. So now let's ask, what about private learning? All right, and so we're going to ask, define the sample complexity of private learning of a concept class to be the smallest n, such that there's a non-trivial differentially private learning algorithm. Say, with the epsilon privacy loss parameter set to be 0.1, and also the confidence and accuracy parameters to be some small constant, 0.1, and delta to be small compared to 1 over n. The particular choices of the parameters here are not so important because they're amplification results that allow us to move from one set of parameters to another. And so the Cleaners paper gave a generic construction of a private learner that said the sample complexity of private learning is upper bounded by log of the size of the concept class. Okay, so this is a very good bound, being only logarithmic, but it's not as good as non-private learning, where, to the question before, the sample complexity is given by the VC dimension, which is less than or equal to, but can be a lot smaller than log of the size of the sample class, concept class. And in particular for threshold functions, the VC dimension is 1, but log of the size of the concept class will be log of the domain size, which is infinite in the case of the real line. So this motivates, understanding when can we improve this bound, and there have been improved algorithms for a number of specific concept classes, simple concept classes like point functions, threshold functions, conjunctions, half spaces, polygons. But what I want to highlight are these recent results that have almost completely answered the question for the case of threshold functions, showing that the sample complexity of differentially private learning of threshold functions is approximately log star of the domain size. So it's at least proportional to log star, and at most log star to the 1.5. So log star being the number of logarithms you need to take to get go from t down to 1. And this is an extremely slowly growing function of t, but it is still growing. And it proves in particular that it's impossible to learn in a differentially private manner, learn threshold functions over infinite domains, in contrast to the non-private case. So this lower bound was shown first for proper learning in joint work with Bunn, Neeson, and Stemmer. And last year, alone, Livni, Maliaras, and Moran obtained a lower bound for improper learning. And if I had more time, I would love to give you a taste of the lower bound, which begins with an application of Ramsey's theorem on hypergraphs, which is where this sort of tower, log star, which is kind of inverse of a tower behavior, comes up. And for the upper bound, I can plug a paper from this conference by Kaplan, Liggett, Mansour, Naor, and Stemmer, which improves the previous bound that was exponential in log star t. All right, so now we almost completely understand the private learnability of threshold functions. Is there anything more general to characterize the learnability of other infinite concept classes? So another brand new result says that the private learnability of a concept class is related to its Littlestone dimension. All right, what is the Littlestone dimension? It characterizes online learning. It's the minimum number d, such that an online learner, that there exists an online learner that never makes more than d mistakes, even against an adversarial sequence of examples. And so it turns out that the sample complexity of privately learning a concept class is sandwiched between log star d and exponential in d, where d is the Littlestone dimension. The lower bound is due to the same paper of Alon et al. That I just mentioned, and is a consequence of the fact that any class of large Littlestone dimension contains a large class of threshold functions. And the upper bound is a very new paper of Bunn, Livni, and Moran. There's, of course, still a huge gap here between the lower bound and upper bound, log star versus exponential. But they still tell us, at least in answer to the question, an infinite class has a private learner if and only if it has finite Littlestone dimension. And obtaining a tighter characterization of the sample complexity of private learning remains an intriguing open problem. Okay, so, and I should just mention that for the case of pure differential privacy, where delta is 0, there is a very nice characterization of the sample complexity of private learning. And what's open here is to characterize it in the case of epsilon delta differential privacy. And again, there's a number of really nice papers here in this conference on differentially private packed learning, shown here on the slide, including the first one of these by Alon et al. Is very related to this relationship between private learning, differentially private learning, and online learning, as you can tell from the title. So let me wrap up and conclude. I hope I've conveyed that there are still many fascinating research challenges for learning theorists in differential privacy, and also that many of these are very relevant to the practice of differential privacy. And finally, just make a pitch. I hope that all of you who are interested in differential privacy will join the OpenDP community, and when the time comes, contribute your algorithms to it. Thank you.
Thank you, Salil, for a very engaging talk. So we have time for questions. Again, if you have more questions for Salil, please type them in the chat box, and I'll actually ask you in this case to read out your questions directly one at a time.
Sure, let me figure out how to open the chat box.
Oh, I meant to the audience, Salil. I didn't mean.
Okay.
Yeah, I'm hoping that people can actually speak up and ask their questions to you if there are any. Okay, so the first one is from Sushant Agarwal. Sushant, are you able to, let me see if I can enable this actually. I think, give me a moment and then you should be able to unmute yourself, Sushant. Yeah, do you want to give it a try?
Oh, hi, am I audible?
Yes.
Yes.
Okay, so I'm just reading out my question. So basically, if I understand correctly, the differential privacy, the privacy guarantee is basically for two neighboring input databases, the output distributions will be similar. The distribution over outputs will be similar. And is there any reason why we restrict the notion of measuring how similar the output distributions are to the one mentioned in the definition of DP? I mean, we could measure similarity by other notions of similarity by, for example, statistical distance or some other reasonable notion of similarity.
Great, thanks for that question. Yes, the choice of how, so we measure the closeness of these distributions, primarily in this multiplicative sense, this e to the epsilon sense. And that choice is quite subtle and important for the semantics, the privacy semantics of the definition, how we interpret it. So without spending too much time, if you just take total variation amounts to setting epsilon to be 0 and just using delta as your privacy parameter, there you run into a situation where if you let delta be too big, say bigger than 1 over n, it allows for algorithms that we really don't consider to be private, like picking a random row from the data set and publishing it. And if you allow it, if you make delta, require delta to be small, like I did, if you only allow this delta parameter smaller than 1 over n, you can't get any utility out of differential privacy. All right, so that's why not total variation. Why specifically this multiplicative? There's a few ways of understanding it. One comes from the multiplicative definition of differential privacy has a very nice Bayesian interpretation, where you can translate it into posterior beliefs on on data set D versus D prime. And the multiplicative definition is really important for that because of, it allows you to it factors through Bayes' rule. That is to say, I mentioned these other forms of different variants of differential privacy that people are studying for the purposes of getting better composition. And they are in the spirit of what you're describing of looking for relaxations with other ways of measuring closeness between distributions. But also, it's important to keep an eye on, are we preserving the privacy protection semantics of the definition that we want?
Okay, yeah, thanks.
Great. There are at least 2 more questions. The next one is from Clement Canon. Clement, are you able to unmute yourself?
Sorry, yes. Yes, so my question was about the one thing you mentioned. So there is that characterization of learnability for differentially private packed learning. And there are similar things for local GP. If I remember correctly, SQ learning, like there's a characterization. Are there similar results for other models of privacy, such as pan privacy or shuffle privacy, or not yet? And is it interesting?
Great. So let me start with the last part. It definitely is interesting. So let me, for others, kind of the first part. So in the original Cleaners paper, they showed something similar to what I described for the local model of privacy. They showed it's characterized by SQ learnability, in the sense that there is a finite sample, and in fact polynomial sample local DP learner, if and only if there's a finite sample or polynomial sample SQ learner. So there is a close relationship there, but it's not, I believe it's not an exact relationship. And so it does not pin down the sample complexity, all right? But it's tighter than the huge gap we have for Littlestone dimension for the centralized model. And that applies to both pure and approximate DP. I don't know. I'm not the right person to ask. There's probably other people at the conference who are more on top of the recent developments in the local model and the shuffle model, how close we are to having tight characterization in those models. And I'm afraid I just don't know the answer off the top of my head.
Okay, great. There are still at least 2 more questions, or yes, 2 more. There's one from Junghyun Lee. Junghyun, are you able to unmute yourself?
Can you hear me? Well?
Yes.
So my question is, in your presentation, you mentioned something about the online learning framework in between. So by online, do you mean that the queries, the set Q is revealed one by one, or is it something else?
Okay, great. So this came up kind of in 2 places in the talk. All right, so let me just start with at the end, where I mentioned a Littlestone dimension, and that as that's a characterization of sample complexity for online learning. That, even though that's about online learning, the theorem I was stating was it was characterizing private learning, not in an online sense, like offline private learning. I don't know if it also characterizes online private learning off the top of my head. It might also, I'm not sure. Earlier in the talk, I also mentioned the use of online learning algorithms for synthetic data generation. There they kind of play 2 roles. One is as a tool. And so you can think of, even if I'm not interested in solving an online problem, using the online learning method is a good way of building the synthetic data internally in my algorithm. However, it is also the case that those methods and this private multiplicative weights algorithm also work in an online setting where the queries are issued one at a time.
Thank you for the answer.
Sure.
Okay, great. There's one more question from Praneeth. Praneeth, are you able to unmute yourself?
Yeah, hi. So my question is, if there is a trade-off between the privacy guarantees, the epsilon delta parameters, and the accuracy that you can obtain?
Oh, yes, yes. Thanks for the question. I wasn't as explicit about that as I perhaps should have been. Let's see if I can. Are my slides still showing?
Yes.
Yes.
Okay. So let me just go to the first place we see it, but it happens a number of places in the talk. So there's many places where I've stated these accuracy bounds, and even also for the Laplace mechanism in the beginning, where you see the privacy parameters appearing in the accuracy bound, right? So, you know, often you'll see epsilon n appearing, or in the local model, you'll see epsilon squared n's, you'll see logarithmic factors depending, like square root log 1 over delta appearing. And those are expressing a privacy accuracy trade-off, meaning to get higher privacy, taking epsilon or delta smaller, it makes your accuracy worse. And in many cases, we know that those trade-offs are tightened. In particular, I mentioned that we know that this bound that I've stated here is tight, and it's tight also in its dependence on epsilon and delta. So it is an inherent privacy accuracy trade-off.
Great, thanks, Ali. Let's take one last question. It's a question from Chapa Chepesvari. Chapa, would you like to come online?
Sure. Very nice talk. Thank you. My question is, you talked a lot about that eventually you want to apply these algorithms practice. So to apply them, you presumably need to choose epsilon in some way. And the question is, what are the considerations that go into choosing epsilon?
That's great. Yeah, it is a thorny question for the field and for applications of differential privacy. So in practice to date, in most of the deployments, the epsilons that have been used are often things that are larger than we as theorists, or me as trained as a cryptographer, are comfortable with. They're not in that range of 0.1, but often it's considered success when they get into the single digits. Okay, and there the privacy guarantee that's given by the definition, saying you're close within a multiplicative factor of e to the epsilon. If epsilon is 5, that's not a very strong promise, right? Nevertheless, I think there is a lot of value still in those approaches, because what they are doing is they're forcing this discipline that was often missing in the past, this idea that you can just release unbounded amounts of statistical information about your data set and privacy will be protected. So what it's doing is still enforcing a budget that forces a limit on how many statistics you release, and or with what accuracy you release them. But there's a lot of engineering work still to be done to bring those numbers down to a more reasonable place. The second part of an answer to your question is this also needs to be a place where the mathematicians, the statisticians, differential privacy folks, experts need to engage with policymakers. And because ultimately, like, what the value of releasing high quality data, highly accurate data, needs to, that has some societal value, as does the protecting the privacy of the data subject has some societal value. And where you strike the balance between these things will differ between contexts, and is not something for us alone as computer scientists to answer, but rather is a conversation we should be part of to help and understand what are the implications of choosing a certain value of epsilon. We've done some writings and working with folks in law, try to understand, give interpretations of the privacy parameters that are a little bit easier for a policymaker to understand, and reason about, try to reason about, how do they fit with legal requirements, but that's a very, tricky question as well.
Mm-hmm. Thank you.
And I see a question here is from Sushant, is epsilon public? Yes, it should be. And the privacy protections don't depend on epsilon being hidden. And in fact, one of the big features of differential privacy is all the parameters of the algorithm and the code for the algorithm itself can be made public. And the only thing that's kept secret, of course, beyond the original data set, is the specific draws of randomness that you use in the algorithm. And that's also very important for for transparency, and when companies have released data without using differential privacy without saying what their epsilons are, they've gotten a fair amount of backlash for lacking that transparency that's supposed to come with differential privacy.
Okay, great. Thanks, Salil, again for a very engaging talk. I'm going to just clap on all of our behalf for being here with us. Thanks also everyone for your questions. So I think at this point, Jake would like to just come and tell us a little bit about the coffee breaks that are to come. And
thanks, everyone.
Okay. Thanks again for joining. Yeah. So Jake, are you there?
Yes, here. Thanks, Salil, again for that. I just want to let everyone know who's still here. We have planned every time after many sessions in keynotes, there's a scheduled coffee break. There's a coffee break now. So a coffee break doesn't have to involve coffee. It can involve other beverages. It can involve no beverages, whatever you like. But the point of the coffee break rooms is that you can show up and just chat with who's ever there. Some of the coffee breaks are manned. If you go into if you click on you may want to refresh the page since we've actually changed the links because of the issues we had earlier. So make sure you refresh the page and you'll see the new coffee break Zoom links. They should be working just fine now. But if you go into some rooms are manned, I think the first coffee break we have, I believe we have Chaba and Gergely who are manning coffee room 1, and the coffee rooms 2, 3, and 4 are open. Anyone can go in. If the coffee break is manned, it just means that you know who at least 1 or 2 people are going to be there, and you know their names. You don't have to be Hungarian to go into coffee room 1. I just want to mention and emphasize that coffee room 5 typically is reserved for grad students. So if you're not a grad student, maybe stay out of coffee room 5. And if you're a grad student, you're welcome to go to all 5 of the coffee rooms. Don't feel restricted to go to room 5. You can go wherever you like. But coffee room 5 will be reserved just for students. So feel free to head over there now. You have an option. Just check the website for the links, and we'll hopefully see many of you drop in for some chit chat. Thanks, everyone. Oh, and also I should mention one last thing. We had some issues earlier on the poster session links. We've resolved those problems now. It seems like that's been fixed. So make sure you refresh the website for those updated links. Things should be all set. See you guys in the coffee break rooms. Thanks.